Hello everyone, welcome to episode 2 of the op-amp tutorial series, Introduction to Op-Amps Part 2. In the last episode, we introduced the operational amplifier, discussed some of its uses and applications, and did a small demonstration with the LM324 op-amp using a power supply as a voltage source and an oscilloscope to measure the signals. In this episode, we will be observing the LM324's behavior over frequency and at different signal amplitudes. So we're moving along to another circuit with a function generator instead of a DC voltage source. It has all the same features as the previous circuit. Function generator as the voltage source, scope channel 1 on the function generator, along with the scope grounds, and everything else is the same. Here, we are connecting up the function generator to the input of our op-amp circuit now, instead of that power supply voltage source. But we're connecting it to this same spot with the channel 1 and channel 2 scope probes in the exact same spot that they were before, and everything else the same. So here I'm turning it on at 100 Hz, and we can see that the voltage levels for channel 1 and channel 2 are about a factor of 2 apart. We've got about 250 millivolts on channel 1 and 500 millivolts on channel 2. They're off by a few millivolts. This is partially due to the accuracy of the scope, partially due to errors in the gain setting resistors, which are not precision resistors, and partially due to other setup-related issues like EMI in the setup causing voltage spikes being picked up by the scope and artificially increasing the peak-to-peak voltage measurement. Both channels are on the same volts per division, which is why they're showing that the channel 2 looks about twice as large as channel 1. So I've set channel 1 to 50 millivolts per division, with channel 2 at 100 millivolts, so that they look like they're on top of each other. So the factor of 2 that we saw in the circuit is now being negated effectively by the scaling factors on the oscilloscope, as with the previous experiment. Here we show that the function generator can change the amplitude of the input signal, and the amplitude of the output signal changes as well. Frequency can also be changed, though we will keep it for this test at 100 Hz. Now, we're going to slowly increase the magnitude to see what happens at higher and higher magnitudes. See if we can see the effect we saw with the DC value. Changing the oscilloscope scaling factors as we go along. Now we're at about 13 volts output. Everything looks pretty good, just like it did before. The signal's a little cleaner because we're now further away from the noise floor of the oscilloscope. Now I'm going to stop changing the scaling factors and keep the two channels at a factor of 2 apart to negate the gain of the amplifier, so that the two channels' signals appear on top of one another. Now we increase it further. Before, it was about 10.8 volts where something started to happen, and so if we assume it's roughly symmetrical on the other side, the volts peak to peak should be about 21.6 when something strange happens. So let's see what happens. So at about 22 volts, we see some flattening in the output. The input looks clean, just as before. The output looks like the tops of the sine wave have been chopped off. It's flattening. because it can't go any higher or lower than a certain point near the rails. Even with higher input voltages, the problem persists. Taking a look at the voltage where that flattening happens, we can see just as before, it's right around 10.8 volts when it flatlines on the high side. And right around negative 11.2 on the low side. So it seems to be able to get closer to the negative rail than to the positive rail. So now we're going to take a look at what happens when we increase the frequency at low amplitude. Here we're at our 100 Hz with the oscilloscope set up so that the scaling factors cancel out the factor of 2 gain from the circuit. So this is fairly low amplitude. The output is less than half a volt peak to peak. 100 Hz, increasing it to 1 kilohertz, adjusting the oscilloscope, time per division, to compensate for the increase in frequency, and we see that the resulting waveform looks very similar, except at a higher frequency. Now increasing to 10 kilohertz, there's a little bit of blue showing up on the bottom portion of the sine wave, making it look like channel 2, which is the output, is lagging behind the input a little, but it is very minor. So now we're going up to 50 kilohertz, and we can definitely see that blue is lagging behind yellow. Since the x-axis is time from left to right, signal content that appears more to the right appears later in time. So since changes in the output, blue, are showing up to the right of the input, yellow, then the output is lagging behind the input. I'm also noting here that the amplitude hasn't really changed much. The two amplitudes have been at around 230 millivolts input and 430 millivolts output. As I mentioned previously, the reason it's not exactly a factor of 2 has to do with inaccuracies in the test setup and a few other factors. Now we're moving the frequency up to 100 kilohertz, and you can see even at 100 kilohertz, there's very little change in the gain of the circuit. And the delay, also called the phase shift between the output and input, is a little more evident, but still not very significant, even at 100 kilohertz. As we keep going, we see that the blue line is getting further phase shifted from the yellow. And now it's starting to shrink. You can start to see it shrink more significantly. This is at about 350 kilohertz, looks like. We keep going, and it's getting close to a gain of 1 from a gain of 2. As you can see, 216 millivolts and 284. At 500 kilohertz, it's almost a gain of 1. We can also note that there's a sharp bottom, sharp top, and the two sides of the waveform appear to be more flat and less gradual, like a proper sine wave. This is a form of distortion that appears to be occurring due to the high frequency. This is very likely what's called slew rate limiting, which is an effect we will explore in later videos. Now the gain is actually below 1, so it's no longer amplifying the signal, and there's a significant phase shift at about 800 kilohertz. At this point, further increases in frequency will only lead to similarly lower gain below 1, and Once the gain is below 1, the amplifier no longer serves as an amplifier, and therefore we don't usually look at what happens at frequencies below the gain of 1 point. But this gives you an idea of how the LM324 behaves over frequency in its configuration. The point at which phase shifts become significant and gain starts to reduce is dependent upon the gain setting resistors as well as the chip itself. So this is not a general bandwidth assessment for the LM324, but it gives you an idea of what it's like with a gain of 2. And of course we will be talking about bandwidth considerations, including how to calculate bandwidth for a given op-amp circuit in later videos. One last thing we'll look at today is a strange effect that occurs when you increase the amplitude and the frequency of an LM324 op-amp. This effect is dependent upon the op-amp in question, and so while it is present for all LM324s, it is not present in all op-amps. But it's a glimpse into the sort of advanced concepts I'll cover in future videos, if you continue on this journey with me and see just how deep the rabbit hole goes. Up until now, we've looked at low amplitude signals at high frequency and high amplitude signals at low frequency, but not both yet. First, we set the output voltage to around 5 volts peak to peak. We could go higher, but it is instructive to see that this effect occurs even when the output voltage is pretty far from the rails. So, we've set the scaling factors of the oscilloscope to negate the gain of 2 so that the two signals go on top of each other again. We're starting off at 100 Hz. Things look good and solid at 100 Hz, which is what we expect for low frequency. Input is 2.62 volts, output is 5.16 volts. At 1 kilohertz, the input is about 2.6 volts, the output is again 5.12 volts, and the waveform looks very similar, as it did at 100 Hz. Now we're running up at 10 kilohertz. Input is 2.64 volts, output is 5.08, pretty close to 5.12 again, but something very strange happens. We see what looks to be small shelves happening, sort of towards the middle of the waveform. So what's happening here? And this is on the output only. The input still looks clean. So here I'm moving the DC offset from the function generator, showing that it does not affect the voltage at which these shelves occur, since you can see it happens at the same points on the y-axis. This effect is called crossover distortion. It is caused by the 2 transistors in the output stage of the LM324. It is a push-pull output, which means that only one of these 2 transistors conducts current at a time. One conducts power only from the high side rail, VCC, while the other conducts power only from the low side rail, VEE. This means that when the output voltage goes from a high voltage to a low voltage, or a low voltage to a high voltage, it has to turn one transistor off while turning the other transistor on as it passes through the middle region. This results in a highly nonlinear region right around that transition point. To make matters worse, loading the output will change the distortion. So here, I'm adding a 10 kilo ohm resistor to the output. Here, I'm going back and forth, so this is loaded, this is unloaded, this is loaded, unloaded. So, if you're using an LM324, you have to be careful about this distortion because, as you can see, it's rather significant, even for a relatively small, large signal. And if you go higher in frequency, here's 50 kilohertz, which, if you recall from the small signal analysis, or the small signal test, looked perfectly fine. There was a little bit of a phase shift, but apart from that, it looked really good. Now here at, looks like 2.32 volts of output, the output looks horrible, horribly distorted. It's very lopsided. You have almost nothing going on the low side, and it's almost the same voltage level as the input voltage. It's actually a little bit lower peak to peak, though it's so distorted that it's hard to call it proper gain at this point. Now all of this is because of the amplitude. is going into what's called the large signal domain, rather than the small signal. Small signals are easier to sustain than large signals. A lot of this has to do with crossover distortion and slew rate limiting, which are both nonlinear effects. You can see that there's significant crossover distortion at 30 kilohertz, with the input at 1.47, output at about 3 volts. But as we drop the amplitude, all that distortion disappears, and we get a nice clean signal again, right at around 1.5 volts maybe. So this effect is highly nonlinear, and highly frequency dependent. Thank you for watching my video. In my next video, we will be starting a more formal study of op-amps with the concept of the ideal op-amp. If you enjoyed this video, please like, share, and subscribe. I'll see you next time.